video we're going to look at the 2019 AS Practicing Chemistry OCR AS paper. I'm going to look at the first 10 multiple choice and talk through the answers to each of those. I'd suggest pausing before I go through each question and having a go yourself, and then having a look at the answer. So first three questions. First one, we have 4 statements and we've got to identify which is the one that is not correct. So 3 of them are going to be correct, 1 of them is going to be incorrect. So I'll just go through them one by one. The elements are arranged in groups with similar chemical properties. That is a true fact. The elements are arranged in periods. They do have repeating trends across periods. And elements are arranged in order of increasing atomic number. That is true. So I'm assuming this one is going to be the false. The elements in the halogen group, which is group 7, increase in reactivity down the group. Well, that is incorrect. They become less reactive as you go down the group. So D is the one that is not correct. Question 2, I would address this one by writing down the shape, and then we have to recall what the bond angle for each of them are. So we have an ethene molecule here. There are 3 bonding pairs, no lone pairs. So we've got a trigonal planar, and within that, the bond angle is 120 degrees. The key word in the question is we're looking for the largest. Water is a non-linear because it's got those lone pairs on the oxygen. So in the non-linear, we have a bond angle of 104.5. Ammonia, again, it's got the lone pair on the nitrogen. It's got the 3 bond pairs, 1 lone pair. So this time the shape is trigonal, but it's a trigonal pyramidal, with the bond angle being at 107. And last one, we've got methane here, which has the 4 bond pairs and no lone pairs, so we have a tetrahedral shape, and within that we have a bond angle of 109.5. So we're looking for the largest one, which is going to be A. Next question, what is the percentage composition by mass of nitrogen in this compound? So we're looking for the formula we're going to use is mass of nitrogen divided by total mass, and then putting the numbers in. We're going to use our periodic table to answer this one. We have got 2 atoms of nitrogen because we've got 1 inside the brackets, then we've got 2 outside, that means we've got 2 atoms of nitrogen. Each nitrogen is 14. So that's a total mass of nitrogen. Then we are going to work out the total mass of ammonium carbonate. So again, we've got to include the nitrogens. So we've just worked out there's 2 nitrogens. So that was mass of 28, 2 times 14. Then hydrogens, mass number is 1, and we have 4 times 2. So we have 8 hydrogen, a mass of 8 for hydrogen. Carbon, we just have the 1 carbon. Looking at the periodic table, the mass number of carbon is 12. And we've got this 3 after the O, means there's 3 oxygen atoms within this compound. So each oxygen is 16. 3 times 16 is 48. Go on to the next stage, 2 times 14 is 28. If we're to add all these numbers up at the bottom, come to 96, and we multiply our answer by 100, and that will come out as 29.16 recurring as a percent. So looking at our answers, our answer is going to be C. Going to question 4, which chemical process is the most sustainable in terms of the atom economy? So sustainable atom economy, so the process that has the highest atom economy is the one that is going to be most sustainable. And the way that we work out the atom economy is the formula of our desired product, or the mass of the desired product, divided by total mass of all products. How do we know which is the desired product? Or we're told the desired product is the organic product. So first thing I'm going to do is just underline the desired organic product in each of the questions. So in A, this is our organic. In B, this is our organic. C is our organic. And D, this is our organic. So we're going to divide, if we take A as an example, we're going to divide the mass, this is our desired product of this alcohol, and divide it by the total mass of all products. So the first thing I'm going to do is work out the mass of both products in question A. So the mass of methanol is 32. The mass of water is 18. So using this equation at the top, desired product is our alcohol. It's going to be 32 over the total product, which is 50. So there, times that by 100, that would give an atom economy of 64%. So that means 64% of the mass of the product is our desired product. Going into B, we're going to work out the mass of this organic product here, halogenoalkane. So this one has a mass of 64.5, so I would do 64.5 divided by the total mass of all of the products. So this one is 64.5, this one is 120.1, and H2O is 18. We add those up, comes to 202.6. Again, we use our atom economy equation, and this comes out as being 31.83%. So we can see at the moment, it's definitely not going to be B because A's got a higher percentage. Question C, the mass of the organic alcohol is 46. NaBr has a mass of 102.9. So we add those two together to get the total. So that's going to be 46 over 148.9 times by 100, and that comes out as 30.89%. Again, it's not higher than A, so that's A's our answer so far. And in the last one, we're going to work out the mass of our organic product. So our organic product here has a mass, this alkene has 48.8, and then we've got water, which is 18. So 48 over 48.8 plus 18 is 66.8 times by 100, and that comes out as being 75.67. So this is going to be our highest atom economy. So our answer is D. Question 5. We have got 8 decimeter cubed of NO mixed with 6 decimeter cubed of O2. We're told it's at room temperature and pressure. The reaction takes place until one of the reactants, so only one of the reactants is used up. So that tells me one of these reactants is in excess. What is the volume of the mixture at room temperature and pressure after the reaction has taken place? So I'm going to rewrite the equation and show some working out below. So I'm going to write the start and at the end, and I'm going to write down the volumes we've got at the start. So the volume of NO is 8 decimeters cubed, that's given in the question. Oxygen is 6 decimeter cubed, and we have 0 decimeter cubed of the product. So I'm looking at the ratio, we've got 2 moles of NO to every 1 mole of oxygen. So if we were to react, let's try and work out which is the one in excess. So if you've got 8 decimeter cubed of NO, we're going to need half the volume to totally react with it. So we're going to need 4 decimeters cubed of oxygen to react it, which we do. So that tells me that tells me oxygen is going to be the one that's going to be in excess. If we look at it from the other way, to react with 6 decimeter cubed of oxygen, we would need 12 decimeter cubed of NO, which we don't. So oxygen is the one in excess. So if we were to use up the whole of the 8 decimeter cubed, we'd have 0 left at the end. To react with the 8 decimeters cubed, we need half the volume because it's got half the number of moles. So we're going to use up 4 decimeters cubed of the oxygen. So if we use up 4, that means we're going to have 2 left at the end. And then if we look at the ratio between NO3 and, so that should be NO2 at the end, we can see the ratio is 2 to 2, so more simply 1 to 1. So if we've got 8 decimeter cubed of this, we're going to have 8 decimeter cubed of this at the end. And then it's just a case of adding up the total volume at the end. So we've got 0, 2, and 8. So 2 plus 8 equals 10. So B is going to be our answer for this one. Question 6. What is the volume of 0.01 moles of nitrogen at 350 degrees Celsius and 200 kilopascals? So this is going to be our ideal gas equation. So we've got a bit of working out to do here. So this is the equation to start. First thing I'm going to do is to rearrange it to get our focus, which is our volume. So to work out volume, it's going to be our nRT over pressure. So first thing we'll do is start inputting the values. So we're given the moles. So N is moles, 0.01. Our constant is our 8.31R, and the temperature. Temperature is given to us in Celsius. We need it in Kelvin. So to put it into Kelvin, we add 273 to it. So that would give our temperature in Kelvin being 623. And our pressure is in kilopascals. I'm going to put it into pascals. So to go from kilopascals to pascals, we times the pressure by 1,000. So 200 times by 1,000 would give pressure of 200,000 pascals. And if we were to put that into the calculator, we get an answer of 0.000258, and our answer is in meters cubed. None of the potential answers are in meters cubed. So first of all, I'm going to convert that into centimeters cubed to see if that comes out with a correct answer. So to convert from meters cubed to centimeters cubed, we're going to multiply this answer by 1,000,000. And that will give an answer in centimeters cubed, and we'll see if it matches up with one of those. So pop that into our calculator and we get an answer of 258.85 centimeters cubed, which is matching up with our B answer. So I would go B for that one. Right, question 7. We are told we've got 0.24 grams of an element and it's reacted with 0.01 moles of chlorine to form a chloride with the formula XCl2. We've got to identify what X is. So the equation I'm going to use to help me with this question is going to be our moles equals mass over mR. So I'm going to use this a couple of times, I think, in this question. So the first thing I'm going to do, the key to this one is we can work out the mass of chlorine we've got by using this equation, because we know the moles, we know the MR of chlorine Cl2 is going to be 71. So if we rearrange this equation to get mass, we will be multiplying moles by the MR, and if we're to do that, moles is 0.01 times by 71 gives mass of, so the mass of chlorine equals 0.71 grams. So then if we look at the next stage, is going to be, we know we can work out what the total mass of the product is. So mass of XCl2 equals, we know we've got 0.71 grams contributed from the chlorine. We're told in the question we've got 0.24 grams of X. So that gives a total of 0.95 grams. So we know that we've got 0.95 grams of XCl2. Looking at this, we've got the ratio between the chlorine and the XCl2 is 1:1. So we know the moles of XCl2 is going to be 0.01 as well. We know the mass, which is 0.95. So we can work out the MR of chlorine, of XCl2, sorry. So the MR of XCl2 is going to be our mass, which is 0.95, divided by the moles that we've got, which is 0.01. So the MR is going to be 95. And then the last step to identify what X is, if the mass of XCl is 95, we can take away the contribution from the two chlorines. So 2 chlorines, 35.5 times 2 equals 71. We take that away from the 95, and X has a mass of 24. So then we look in the periodic table, which one of these has a mass of 24, and magnesium is the one. Phosphate iron has the formula PO4 3-. We've got to identify what the formula for copper 1-phosphate 5 is. So the clue is in this Roman numeral after it. So copper with a 1 Roman numeral after it means it's got a charge of +1. The phosphate iron has 3-. These charges are not equal, so we need to equal the 3 minuses by adding more coppers. We're going to need 3 coppers in total. The only one that's got 3 copper is going to be D. Then which reaction shows chlorine only being oxidized? So oxidized is loss of electrons. So when something loses electrons, the oxidation state is going to become more positive because it doesn't have as many of the negative electrons. So we've got to identify a reaction where chlorine is only being oxidized. So I'm just going to go through the oxidation states of each of those. So chlorine is 0 in this one, -1 there, and within HClO is +1. So this one example, chlorine has been oxidized from Cl2 to HClO, but it's also been reduced as well. So it's not going to be this one because it's been both oxidized and reduced. At ClO2, we've got a +4 on the chlorine. In NaClO2, it's going to be a +3. And in NaClO3, it is +5. So again, this one is not going to be correct because the chlorine has been oxidized into the NaClO3 and it's also been reduced to NaClO2. So it's not just being oxidized, it's been reduced as well. In the next one, we have a +5 charge on the Cl in this compound. In the two products, we have +7 and -1. So again, going from the reactant to the product is being both reduced and oxidized because the oxidation number is increased and it's being reduced there. So it's going to be not that one, so it's probably going to be D. So let's just confirm that in MnO2, sorry, in HCl the oxidation state is -1. In MnCl2 it's also going to be -1, and in Cl2 it's 0. So we can see the oxidation state hasn't changed when it's gone into MnCl2, but when it's gone from HCl to Cl2, it has become more positive, which means it's lost one electron, so it's been oxidized. There is no situation where it's been reduced, so this one would be our answer. And the last question in this part of the video is this question about reversible reaction. We've got the enthalpy profile diagram shown below. We've got some statements. We've got to identify which one is correct. So the activation energy of the forward reaction is 120. Activation energy is this line here. We've got an answer 150 there, so this one is not correct. The activation energy of the reverse reaction is 270. So if we start from here and go all the way to the top, the total energy is 120 plus 150, which does equal 270. So this one is my favourite one so far. Question C, the enthalpy change of the forward reaction is -30. Enthalpy change is from the reactants to the products, which has an answer of 120. So this one is incorrect. And the reverse reaction is exothermic. So we can see the forward reaction is losing energy to the surroundings because the energy of the products is less. So the forward is exothermic. Therefore, the reverse has to be endothermic. So therefore, this one is also incorrect, leaving B as our correct answer in this playlist. So first up, hydrogen and chlorine reactor shown below. We've got balance equation. We've got delta H is -184.6 kilojoules per mole. Which statement about this reaction is correct? So 3 of them are going to be false, 1 of them is going to be incorrect. So less energy is released on bond making than is taken in during bond breaking. That one is false, because if less energy is released, the energy released on bond making has a negative value, and the energy taken in to break bonds in the reactants is positive. If less energy is released, then this number is going to be smaller than the energy required to break these. Therefore, we'd have a positive value at the end, which we don't. So we know that more energy is released when the bonds in HCl are made. Second one, the enthalpy change for the reverse reaction is 184.6. That looks like it's going to be true because the forward direction is -184.6. So in the reverse has to be the opposite. The enthalpy change of formation of HCl is -184.6. First thought that might seem correct, but the clue is we've got the 2 there. So that means to form 2 moles of HCl, it gives out this much energy. So if we had 1 mole, it'd be half as much, 92.3 kilojoules per mole. So that's why that one is incorrect. And the temperature decreases during the reaction. Well, we can see it's an exothermic reaction because we have a negative value there. So energy is released into the surroundings, so the temperature would increase. So therefore, it has to be B. Question 12. What is the main reason for the increase in reaction rate with increasing temperature? So you can see that in bold, they've put the word main in bold. So there are more than one reason. What's the main reason? So the activation energy decreases. Increasing temperature doesn't decrease the activation energy. the activation energy increases, which you said it doesn't change the activation energy level. More molecules have an energy greater than the activation energy. I'm thinking that that one is going to be our answer, because increasing the temperature, molecules will have more energy, and therefore more of them will have a greater energy than the activation energy. And the molecules collide more frequently, although they will, as we go back to this underlined bold word main. It's not the main reason. So just to summarize, activation energy has a greater effect than collision theory when we increase the temperature. Going on to number 13. A catalyst is added to a system in equilibrium. What's the effect on the rates of the forward and reverse reactions? Well, we've got 4, so again we're going to look for the one that is true. There is no effect on the rate in either direction. Well, that's not true, because catalyst would affect the rate. And looking at the second one, both rates increase by the same factor. That one is true. It would increase the forward and the reverse in exactly the same factor. The rate in the forward direction increases by a greater factor than the reverse, but we just said it will increase by the same factor, so that was not true. And then the rate in the reverse increases by a greater factor than the forward. Note, so when you add a catalyst, it increases the forward and the reverse by the same factor. So this one has to be B. Going on to question 14. What is the best description for the bonding between carbon atoms in an ethene? So in ethene, we have a carbon-carbon double bond. And just a reminder, if we've got a single bond, we have a sigma bond. If we've got a double, we have 1 sigma and 1 pi. So that is going to be A. Question 15. So which compound is unsaturated, alicyclic, and contains an alkyl group? So the way I would do that one is I'd maybe put these little headings here. Unsaturated, alicyclic, and alkyl group, and then go through each of these. So if it's unsaturated, it's going to have a double bond. This one definitely has a double bond, so yep. This one, there are no double bonds in B. Yes, we've got a double bond there, and we've got a double bond in D. So at the moment, we've ruled out B. Alicyclic means it has a ring structure that is not aromatic. Benzene ring is aromatic, so it's not going to be A. Then we have a ring structure there. So we've ruled that A. Now lastly, we've got to look for an alkyl group. So an alkyl group is something like a CH3 or a C2H5 within it. So here we've got a CH3, so that one does have an alkyl group. This one has an alkyl group too. This one does too. This one does. This is not an alkyl group. It's got a double bond there, so that's not an alkyl group. So the only one that fits all three is C. Which statement about an electrophile is correct? So when we're talking about an electrophile, I'm just going to use E. It doesn't represent, just a generic symbol for E for electrophile. An electrophile have a positive charge, because the word electrophile, electro, it's going to have to do with electrons, and phile means to love. It loves electrons, therefore itself is going to be positive because it's going to be attracted to those negative ions. So it is an electron pair acceptor. It accepts electrons because itself is positive. Is a proton donor. It doesn't donate, and it is negative ion, where we can see it's not a negative ion, it's a positive charge. It is a species with an unpaired electron. It's not. It's a positive charge. So an electrophile is an electron pair acceptor. Question 17, we're given a section of a polymer and we've got to identify which monomer could form this polymer. So the best way to approach this is to identify the repeating unit and then convert that into a monomer. So I think this is going to be our repeating unit. Then we've got a second one there. And there's our third repeating unit. So we can see they're all the same. We've got 1, 2, 3 carbons, 1, 2, 3, 1, 2, 3, and they're exactly the same. So then I'm just going to redraw it. So we've got one carbon there. We've got a second carbon there. And then we've got attached to a third carbon and a triple bond to the end. This in the polymer is the single bond, but it's come from a double bond. So this is going to be our double bond between these two carbons, which are these two here. So there's our double bond there. And then it's a case of putting in the appropriate numbers of hydrogens. And then let's write it in this format. So we'll have CH2, CH, CN, and hopefully this matches up with one of those. Well, we can see in A and B there's no double bonds, so it definitely can't be those two. And this one, here we got this one, it matches up with this one. So it looks like it's going to be C. So the answer is C. Which compound is not likely to have a fragment ion at mass charge 43 in its mass spectrum? So OCR like to do the ones where you've got 3 correct answers and one of them is incorrect. So which one's not likely to have a fragment? So let's, if we were to break it there, this side would have 12 carbon is 12, the remainder carbon is 12, hydrogen is 1, oxygen is mass 16. So 12, 24, 28, 29, so it's not that side. This side, if we've got 2 oxygens, that's 32, plus carbon is 44, that's 45. There's no other way of splitting it to get anywhere near, so I don't think it's A. Let's have a look at B. If we were to split it down there, this side definitely doesn't. This side that's exactly the same as that one. It's going to be too much. What if we split off in this point here? So then we've just got that, and we've got 2 carbons is 24, plus 16 is 40, and 1, 2, 3. So this one could have a peak of 43. This one, if we've got these 3 carbons, if we cut it there, 12, 24, 36, and then we've got 1, 2, 3, 4, 7 hydrogens. 36 plus 7 is 43, so that one does have a peak of 43. And this one can have exactly the same fragment. If we break it there, we've got our 3 carbons and 7 hydrogens, so that will have a peak of 43. So the one that doesn't is A. Penultimate question, which statement about infrared, again, it's not correct, so 3 of them are correct, one of them is not. The energy from infrared radiation causes covalent bonds to vibrate more. That's true. So it's not A, because that one's true. Absorption of infrared radiation by some atmospheric gases is linked by some scientists to global warming. Yeah, that is true. For example, carbon dioxide can absorb infrared radiation, so that one is true. Infrared radiation is used to monitor gases causing air pollution. That is a true statement as well. The action of infrared radiation of CFCs in the upper atmosphere leads to the formation of chlorine radicals. It's not as UV that leads to the formation of chlorine radicals. So even if you weren't sure about those, this is the clear incorrect answer. So D, and then last up is we've got an unknown compound produces the infrared spectrum below. Which compound could have produced the infrared spectrum? So, first thing that draws my attention is this peak here. This tells me we have an OH. And it tells me it's in an alcohol rather than a carboxylic acid, because if it was in a carboxylic acid, it would be really broad, which means it's really wide, which would be something like so. So if we had a carboxylic acid, it would be much wider. So that tells me we don't have a carboxylic acid because we've got a much narrower OH. We've definitely got an OH group. So it could be this one. It also could be this one. It's not going to be this one because we don't have an OH group. And the second key piece of information is this peak here. This tells me we have a double bond to an O, C double bond O. If we quickly look at the data booklet, spin it around, we can see in the region of 1640 to 1750, which is where this is, we have a CO double bond. So it could be this one. We've got a CO double bond there. It could be this one. We've got a CO double bond there. We don't have a CO double bond there. And it could be this one because we've got a CO double bond there. So the only one that matches for both peaks is B. So our answer for this one is B. Reminder, you will always get this data booklet in your exam, so it's worth practicing when you're going through these questions. Right, on to the longer questions. There's many different parts to each of the questions. So question 21 is about atomic structure and compounds of calcium, nitrogen and oxygen. Most elements contain different isotopes and state two differences between isotopes of the same element. Well, by definition, isotope with different numbers of neutrons. So the number of neutrons is going to be different. Another difference, if we've got different numbers of neutrons, then the mass number is going to be different. Next thing we're going to look at is we've got a table for an atom and an ion. So looking at the charge, this is going to be our atom because atoms have no charge because they have the same number of protons as electrons. And this bottom line is going to be our ion because it's got a charge of -2. And then we just got to fill in the blanks. So an atom has the same numbers of protons as electrons, so it's got to have to be 26. Our mass number is protons plus neutrons, which is 54. And then if we look in the periodic table, look at the atomic number, find the atomic number 26, and the element that has an atomic number of 26 is iron. Next thing we're going to look at is our ion at the bottom. So we're told we've got 36 electrons and the charge is 2-. So that means there's 2 more electrons than protons. So if we've got 36 electrons, we're going to have 34 protons. To work out the numbers of neutrons is protons plus, to work out the mass number is protons plus neutrons. So therefore, to work out neutrons, we've got to take the number of protons away from the mass number. So 80 take away 34 is 46. Again, we look in the periodic table, find the element that has an atomic number of 34, and we see that is selenium. Going on to the next one, Electrons occupy orbitals, energy levels. Each box represents an orbital, which can contain 2 electrons, and each of these arrows represents one of the electrons. We've got to label the subshells, so let's do that first. We've got 1s, 2s, and 2p. And then what we've got to do, label the subshells and add arrows to show how electrons occupy orbitals in an atom of oxygen. So looking at the periodic table, oxygen has 8 electrons. So we've got 2 there. We're going to 2 there, so that's 4 in total. 5, 6, 7, and 8. We don't put 2 in this one and 2 in this one. It would be we fill 1 in this one first, 1 in this orbital, 1 in this orbital, and then we start filling in the second one. But we stop once we've got to 8 electrons. So we've got 1, 2, 3, 4, 5, 6, 7, 8 electrons. In part D, we've got calcium reacts with nitrogen to form calcium nitride, and this is an ionic compound. Construct a dot cross diagram for calcium nitride. Show outer electrons only and charges on each ion. First of all, I'm just going to draw the atom just so we can see how we can form the ions. So first of all, calcium. And answer the question, I'm just going to show the outer electrons. I'm not going to show all the electrons in calcium. So calcium is in group 2. I'm going to show 2 electrons on the outer shell. And then nitrogen is in group 5. Therefore, it's got those 5 electrons on the outer shell. 2, 3, 4, and 5. So then when it comes to showing the ionic bonding, the thing we're going to do, put the square brackets. The calcium atom is going to lose these 2 outer shell electrons. Because it's lost 2 electrons, it means it has 2 fewer electrons than protons. So it's got more protons, so it's going to have a +2 charge. And if we look at the formula of calcium nitride, we're going to put a big 3 there because there's 3 calciums in calcium nitride. Then coming on to the nitrogen, just going to redraw them because the nitrogen is going to be gaining electrons, but it already has those 5. So we've got to check how many electrons the calcium is going to lose. So each calcium has lost 2 electrons, and there's 3 calciums in total. So there's 6 electrons that are going to be lost. And we can see we've got 1, 2, 3, 4, 5 in the outer shell of nitrogen. 3 are going to go there. And if we look at the formula, we've got 2 nitrogens, so we've got a big 2 there. Each of those nitrogens is going to gain 3 electrons. So therefore, that's where those 6 from the calcium have gone to 3 to each of the nitrogens. We also need to make sure that we put the correct charge on the nitrogen. So each nitrogen has gained 3 electrons. So therefore, it's going to be a 3- charge. Next thing we're going to do, again we're using calcium nitride, reacts with water to form a solution containing 2 alkaline compounds. Write an equation. So we've been given the formula of calcium nitride. We react it with water. Then we are got 2 alkalines. So calcium hydroxide would probably be 1. So calcium, remember, it's got +2 charge. OH, it's got -1 charge. So therefore, we're going to need 2 of these OHs to construct the formula of calcium hydroxide. And then another alkaline, we've got nitrogen, hydrogen, we're going to form ammonia. Ammonia is an alkaline product. But we haven't quite finished, we need to balance this first. So let's balance the calciums. So we've got 3 calciums this side, we've got 1 this side. Big 3 before that. Let's do the nitrogens, we've got 2 there, we've got 1 there, I'm going to put 2 there. And then we're going to add the appropriate numbers of water to balance the hydrogens and oxygens. So we've got 6 hydrogens, and then we've got 6 hydrogens there, so we've got 12 hydrogens on this side. So we're going to balance with a 6 there. That means we've got 6 oxygens on the left-hand side, and on the right-hand side we've got 2 times 3, 6. So that's the balanced equation for that reaction. Now, calcium reacts with oxygen to form a compound which has a giant ionic lattice structure. The diagram shows ions as circles in part of the lattice. We've got to complete the diagram by showing the symbols of the ions. So first of all, we need to check what the formula of calcium oxide is. So calcium, as we did in the last question, has a +2 charge. Oxygen has a -2 charge. So therefore, the formula of calcium oxide, the ratio of the ions is going to be 1 to 1. So in this, the calcium and oxygen ions are going to be alternating. And then going up to the top, we've got calcium, oxygen. Make sure we put the charges on each of the ions. And then, next part of this question, nitrogen forms an oxide with the formula N2O. A molecule of N2O is linear. Let's underline that, it's going to be key, give us the shape, and has a nitrogen in the center. Draw a dot cost diagram for an N2O molecule. So this is going to be a covalent, drawing this sharing of electrons, whereas the one at the top was the ionic. So we're told that one of the nitrogens is in the center. Therefore, one of the oxygens is going to be on the one side. It doesn't matter which way round you do the outer nitrogen and oxygen, as long as in the middle we've got a nitrogen. And we're told it's linear, so there's going to be no outer shell electrons on the nitrogen in the middle. So as we looked at in the previous question, nitrogen has got 5 electrons in its outer shell. This nitrogen in the middle is going to have to share 3 with this outer shell, with the outer nitrogen. So therefore I think this is going to be a triple bond. So I think from this one we've got the 2 electrons, 3 of them are going to be involved in the bonding. This nitrogen in the center is going to share 3 back. So this nitrogen has got 8 electrons in its outer shell. This nitrogen here has got 2 more. We're told that there aren't any, it's a linear shape, so there aren't going to be any lone pairs to make it into a non-linear shape. So there's definitely going to be 2 involved with the oxygen's covalent bond. And this oxygen has got 6 electrons in the outer shell, it's group 6. So I'm not actually going to share any back. This is a dative bond, because if I was to put 2 of these electrons in there, then this nitrogen in the middle will have too many electrons. So this is going to be our dative bond, where one of the atoms is sharing both electrons in the bond, and this is a triple bond. This is quite a tricky question, but this is what this structure would look like. Question 22, titrations. There will be some calculations in this one. We're told we've got hydrochloric acid and sodium carbonate. We're given the balanced equation, which is useful when we look at the ratios later of moles. We're told we've prepared the sodium carbonate, we're given the concentration, the volume, hydrochloric is added to the burette. The student uses 25 centimeters cubed of the sodium carbonate, and then we've got the burette readings. The rough one has been omitted. The first thing we've got to do is complete a table. So many times I've seen marks lost on this, not because the calculations are wrong, but because you're missing something off. So first thing we've got our initial reading, final reading, difference between the two. So many times students just leaving it like that. Automatically that would be marked wrong, because we've gone to 2 decimal places there, we've only gone to 1 there. You have to put the 0 there. Similarly for this one, difference between the 2 would be 23.85, and the last one, difference is 24.3. Again, leaving it like that would be marked wrong for that, even though you've done the calculation correctly. Got to put that 0 at the end. and then calculate the mean titration of HCl to the nearest 0.05 centimetre cubed that the student should use for analysing the results. So we're looking for concordant results, so I would use that one and ignore that one. So add these two together, 24.2 plus 24.3, 0 divided by 2 would give 24.25, and we're probably going to be using this sometime later in the calculation. Calculate the concentration of the hydrochloric acid, and we've got to give it to 3 significant figures. So first of all, we can't calculate the concentration first up of HCl, we've got to use our sodium carbonate. So we're told the concentration is 0.5. We use 25 centimeters cubed, so I'm going to use that volume, and to work out the moles of sodium carbonate is going to be times volume, which would equal the concentration, which I said is 0.150 times the volume. We got 25 centimeters cubed, so we're going to convert that into decimeters by dividing it by 1,000. So 25 centimeters cubed divided by 1,000 would be 0.025, and that's decimeters, and that would give us the number of moles in that 25 centimeter cubed of the sodium carbonate. Oops, I missed a 0 off there. So we've got that number of moles, 0.00375. Now we can go on and work out the concentration of the hydrochloric acid, because we've been given the balanced symbol equation. So as we said, we've got 0.00375 moles of sodium carbonate. Ratio of sodium carbonate to HCl is 1 to 2. So for every 1 mole of sodium carbonate we've got 2 moles of HCl. So simply multiplying 0.00375 by 2 gives us the moles of HCl. Equals 0.00, and that comes out as 0.075. Now we can use this equation again, because we know the moles, we know the volume, which we've worked out that we're going to use in our calculation, 24.25, and that will give us the concentration. So rearranging that equation, concentration equals moles over volume. So moles we just worked out is 0.0075 over, remember this is the 24.25 has got to be in decimeters, so we can divide this value by 1,000 to get it into decimeters. It would be 0.02425, and that comes out to 3 significant figures, 0.309, and that's going to be, and then the units would probably be on there. We just put our answer 0.309, and that would be our concentration of HCl. There's another part to it. In the titration, the student measured volumes with a pipette and burette. The pipette has an uncertainty of plus minus 0.04 centimeter cubed in the volume measured, and the burette has an uncertainty of plus or minus 0.05. Determine whether the volume measured by the pipette or the volume measured by the burette has the greater percentage uncertainty. So for 2 marks, it's going to be 1 mark for each calculation. So pipette is going to be the uncertainty 0.04 over the volume that was measured by the pipette. So if we go back to the pipette, so the student pipettes 25 centimeters cubed, So the uncertainty is going to be 0.04 over 25 times by 100, and that gives an uncertainty of 0.16. For the burette, it's going to be 0.05. So let's go up to the burette, and the burette volume that we used was for the HCl, and it's going to be this value, the 24.25. But one thing we've got to note is we read off the burette twice, once for the initial reading and once for the final reading. So that we show that in the equation, the uncertainty is 0.05 times 2, because once for the initial and once for the final, over the volume that was read, which was 24.25 times by 100, gives an uncertainty of 0.41%. So you can see that the burette. Question 23, we've got a question about halogens and halides. It's the group 7 elements. Boiling points of halogens shown in the table. They're given in Kelvin, as we can see that the boiling point increases as you go down the group, and we've got to explain the trend. So it's not asking us to describe it. We don't need to talk about as you go down the group the boiling point increases. We just need to explain why that happens, and that is down to the intermolecular forces. So the number of electrons increase down the group, therefore an increase in number of London forces, therefore increase energy required to overcome intermolecular forces. Just make sure you've written intermolecular, not intra. Intra is within, inter is between molecules. Part B, we are supplied with a sample of ammonium bromide. Describe simple tests that will identify the cation and anion present in ammonium bromide. We have to reagents, observations, and the equations. So we'll start with the cations are positive, so that's going to be the ammonium. So how can we identify the ammonium within this? So we've got to do our reagents. We're going to heat it with a hydroxide. Then our observation, we could use indicator paper, and that will turn a blue or purple colour. And then we've got to include our equation for this. So we've got our ammonium, we've got our hydroxide ion, and then that's going to form, it turns a bluey purple colour because of the ammonia, and we've got water as well. Notice there's lots of lines here. I'm not writing in paragraphs, I'm writing in bullet points. And then for the anion, which is going to be our bromide, it's probably the easier one of the two to recall the reagents, observations, and reactions. So we're going to react it with silver nitrate. We would have a cream precipitate, and the reaction for this would be our silver ion reacting with the bromide ion to form silver bromide. That's what causes or creates the cream colour. So question 24 is about ammonia, and we've got a question: in industry, ammonia is made from nitrogen and hydrogen. This is a reversible reaction as shown in the equation below, and we're given the formation, how ammonia is formed, enthalpy change minus 92 kilojoules per mole. Explain how Le Chatelier's principle can be used to predict the conditions of temperature and pressure for a maximum equilibrium yield. So we've got 4 marks there. So I'm just going to put a little subheading first of all, what we're going to write for temperature to maximum equilibrium yield. So temperature, we would need a low temperature because having a low temperature favours the exothermic direction of the reaction. We can see this is exothermic in the forward, so if we have a lower temperature, it's going to favour the forward and increase the yield of ammonia. So temperature will have a low temperature because forward is exothermic. Then for pressure, the way we determine the effect of increasing or decreasing pressures, looking at the moles of gas on either side. So we've got 1 mole of nitrogen, 3 moles of hydrogen. So we've got 4 moles on this side, and on the right hand side we've got 2 moles of ammonia. So if we increase the pressure, we favour the side that has the least number of moles. So if we have, in this case, a higher pressure, it will favour the forward direction because we have less molecules or moles of gas on the right hand side. Again, I haven't written in long paragraphs, just writing the answers in bullet points. Now we've got part 2. Under certain conditions, equilibrium 24.1 has the equilibrium concentrations in the table below. We've got to calculate the numerical value for Kc. So, as a reminder, Kc is our products over reactants. So we're going to have our NH3, and let me just show the equation, because the equation we're going to have 2 outside the brackets because we've got 2 moles of the ammonia, and then we've got to have nitrogen, we have 1 mole, so we don't need anything outside the brackets, and then for hydrogen we have 3 moles of hydrogen, and then we input the numbers, so 0.862 for nitrogen. We're just taking these values from the table, and then for hydrogen we have got 2.75. So using our calculator, it just says appropriate number of significant figures, and it's got to be in standard form as well. I'm just going to go to 3 significant figures, and there we've got our answer for part 2. Going on to question B. Ammonia is used to make nitric acid. First stage is given below. We're given some enthalpy change of formation values. And we've just got to state the conditions of temperature and pressure used for standard enthalpy measurement. So temperature, if you're going in degrees Celsius, is 25, and standard pressure is 100 kilopascals. Now, what would we do? Calculate the standard enthalpy change of formation of NO, give your answer to a whole number. So looking at this, we're given enthalpy change of formation of ammonia, oxygen is 0, H2O, and we're given the overall, so we've got to try and work it out for ammonia. So just as a reminder, it's going to be our products minus reactants, and then we're going to input our numbers. So our products, we've got 6 lots of water. We have got 4 lots of NO, and we're going to take that away from, or we're going to take the products away from it. So we've got 4 lots of 4 moles of ammonia. We're not going to include oxygen's value of 0, and then that will equal our minus 908. So we're going to try and work out what NO is. So let's input some numbers. So for water, we've got 6 lots of water. We're using the value in the table, 6 times 242. We don't have the value for NO at the moment, and we're going to minus 4 lots of ammonia. So that should be minus 242, and then NH3 is minus 46, and that equals minus 908. Let's multiply that, so that is 6 times minus 242 is minus 1452 plus 4NO minus 4 times minus 46 is, put that into brackets, 4 times minus 46 is minus 184, and that equals minus 908. So let's move out of the equation. So we've got minus 1452 plus 4NO minus minus is plus 184.5 is about alcohols and alkanes. We've got 3 alcohols, A, B, and C. They're all structural isomers. They all have 4 carbons, 10 hydrogens, and 1 oxygen. Each alcohol is refluxed with its oxidizing agent, acidified dichromate. And we've got to draw the structures of the organic products. So first of all, let's determine whether we've got primary, secondary, or tertiary. So the first one is primary, because the carbon that's attached to the OH is only attached to 1 other carbon. This one, B, this is a tertiary, because this carbon here, which is attached to the OH, is attached to 1, 2, 3. So this is going to be a tertiary. And then this one here, this OH, is attached to this carbon, which is attached to 1, 2. So this one is going to be a secondary. So if we oxidize and reflux a primary alcohol, we're going to form a carboxylic acid. So we got to do, got our O, still got our OH, got that there, and then we're going to have our carboxylic acid there. Tertiary cannot be oxidized, as it says, if no reaction is going to take place, but none. And a secondary can be oxidized as far as a ketone. So that OH becomes a double bond O. Write the systematic name for alcohol C. So the longest carbon chain is 1, 2, 3, 4. So we're going to have butane, and then this OH, if we count from this end, it's on the 3rd carbon, but if we count from this end, it's going to be on number 1, number 2. It's going to be on the 2nd carbon. We want the number to be as low as possible, so it's going to be butane 2-ol. Complete the equation below for the complete combustion of alcohol at A. So when you combust something, it's got to be in the presence of oxygen, and you're going to form carbon dioxide and water. Now let's try and balance the carbons first. We've got 4 carbons. Let's balance the waters. So we've got 10 hydrogens, so we're going to have 5 waters. And now we just need to balance the oxygens. So we've got 8 oxygens, and here we have got 13. 5 plus 8 is 13. We've got 1 there, so we need 12 oxygens here. So I'm going to put a 6, and that should be balanced. I think this is the last question in the paper. So under suitable conditions, butane reacts with chlorine by radical substitution. A mixture of organic compounds is formed, including CH4H9Cl and compounds DNA. Complete the table below to show the mechanism for the initiation and propagation. So when we're talking about initiation, we're going to use it for chlorine. It's going to break down into 2 Cl free radicals. And the conditions required is going to be UV light. Propagation is where we react one of those free radicals with our C4H10. That will remove one of the hydrogens. This would be a free radical and form HCl. This C4H9 free radical will react with a molecule of Cl2 to form our C4H9Cl, and it will regenerate another free radical. Organic compound D is formed by substitution of all of the hydrogens in butane by chlorine atoms. Write the equation for the formation of compound D from butane. Use molecular formula. So we've got, well, we start with butane because that's what we have. C4H10, and we're told that all of the hydrogens are substituted by chlorine, so we're going to have C4Cl10. We're going to need, and we're going to form HCl, so each of the stages forms a HCl. So how many, so there's going to be 10 stages, so we're going to have 10 HCl. One is going to be formed each time a Cl is substituted on for a hydrogen, and then we just got to balance it with the correct number of chlorines. So this side we've got 10, we've got 20 chlorine on the right hand side. We've got 2, so we've got a 10 before that. That means we've got 20 chlorines. And the very last question is a calculation for 3 marks. Compound E is formed by the substitution of some of the hydrogen atoms in butane by chlorine atoms. Chemists found that 0.636 of compound E has a volume of 78 centimeters cubed. We're given a molar gas volume, and we've got to determine the molecular formula of compound E. So, first thing we're going to do is work out the moles of the gas. So we're going to do that by, we know we've got a volume, so it's going to be the volume we've got divided by the molar volume, which we're given as 32.5. However, this is in centimeters cubed, this is in decimeters cubed. So I'm going to convert the 78 centimeters cubed into decimeters by dividing it by 1,000. So that's going to be 0.78 over 22.5. So we have got 0.0024 moles of compound E. So now what we can do is, using moles equals mass over mR, we can rearrange that to get mass over moles equals mR, because we know what mass we've got. We've got 0.636 grams divided by the moles we've just got, 0.0024, and that would give 265. So we know that our compound E has a molecular mass of 265. Now it's a case of trying to work out how many of those hydrogens have been substituted by chlorine. This might be a little bit of trial and error. So if we've got C4H5Cl5, so in this one, 5 of the hydrogens have been substituted off for chlorines. Let's work out what the molecular mass of this is. So at the bottom, I put carbon is 12, hydrogen is 1, and chlorine is 35.5. So if we're to calculate the molecular mass of this one, 4 carbons is 48, plus 5 hydrogens, and put this in my calculator, 35.5 times 5, add that all up, that comes up to a molecular mass of 230.5, so that's not right. It needs to be higher, so I think we need to substitute more chlorines. So the next one, C4H4Cl6. So the molecular mass, we've got 1 more chlorine, so we add 35.5 onto that, which would be 266. But we've lost 1 hydrogen, so that's going to be 1 lower. So that's going to be 265. So the molecular formula is C4H4Cl6.